So we're talking again about a ring of width delta r, radius r star, at position x along the x-axis, and the contribution to the gravitational field at a point big X. Now I can draw something I really couldn't draw in class because of the lack of resolution. If I just do a bunch of pairs of symmetric points, didn't do a real good job of that, but we've got to have R vectors, and I'm not going to draw the entire R vector here, but we're going to have a bunch of R vectors along these lines, giving rise to field contributions that sort of make a bundle of vectors. And I'm not sure I've got the right number of these, but we see kind of a bundle of vectors indicating the contributions of little mass, little volume increments around this ring to the net gravitational field that results from this ring. Now I've also, okay, we see this bundle. This bundle actually kind of circles this point and revolves around a cone. There's a bundle of vectors that kind of make a cone here. And each vector in that cone has a vector opposite, a vector symmetric with respect to the x-axis, a vector symmetric to it with respect to the x-axis, so that again the j and k components just divide out as we move around that cone. Whether you see that or not, it is a justification for getting rid of everything but the I component. The area of this ring, as we see it here, is just going to be its circumference multiplied by its thickness, which is 2 pi r star times delta r. We also postulate a thickness delta x, because otherwise we're not going to get any volume. Remember, at the end of the last clip, I kind of left the delta v kind of hanging there without being specific about it. So we're going to be specific here. We're going to also postulate a thickness delta x. Now, due to the resolution of the board, I didn't attempt to do that, but I've made sort of a picture here that indicates the kind of region we're talking about. Okay, it's this ring, so we see the ring around here, and it has a thickness that I'll call delta x. So the thickness is delta x, the width of the ring is delta r, and the radius of the ring is r star, so its circumference is 2 pi r star. Okay, well, then the volume of that ring is just its area multiplied by its width, 2 pi r star delta r times delta x. So that our delta gx for the ring, and maybe I should and I'm kind of using the word ring lightly. It's a ring, three-dimensional ring with volume. Sometimes a ring is two-dimensional, and I'm not even sure if there's a convention on just what a ring is. Okay, anyhow, delta gx of the ring is then going to be big G times the expression we've seen already, only the I component of the R vector divided by the magnitude of the R vector, well, by the 3/2 power of the magnitude of the R vector. I'm sorry, by the cube of the magnitude of the R vector, the magnitude of the R vector being the 1/2 power of what you see inside here. And we had our delta V before. When I did this in class, and you might have picked up on it, I wrote a delta M here, kind of losing track of the fact that I'd written a rho over here, and it's the rho delta V that gives you the delta M. So I should have written delta V here, or left the rho out when I wrote the delta M. In any case, this expression is now correct. Our delta M is just rho times 2 pi r star delta r, just rho times volume. Okay, so the rho times the volume is replaced by this, and then we get the expression for the entire circular disk, where we integrate from 0 to r with respect to r. We integrate these ring contributions, letting r become our variable of integration in the obvious sense. We just think of rings expanding out here, ring upon ring upon ring, and then we let the thickness approach 0, delta r approaches r. And for the entire circular disk, we then get the integral of this expression. And I'm going to go ahead and write that in. That's big X minus little x times I divided by the quantity big X minus little x squared plus r squared. And then that's going to be to the 3/2. And that kind of interferes with my parenthesis there. But yeah, you should be able to see or figure out exactly what I've written here. And then that's going to be multiplied by delta x, and then times big G times rho. Okay, so that's a single integral for the contribution from this three-dimensional ring. Now, in order to get the entire field, we have to sum this over all delta x's from the left to the right. In other words, we have the entire cylinder, we've got the contribution from this ring, and now we have to sum that from x equals negative L over 2 to L over 2. And that's going to give us what I've written down here, and what I've got to kind of fix a little bit because it got kind of jumbled up. Again, I didn't predict very well when I wrote this. So I'm going to kind of rewrite the parts of the right-hand side of the board here. Okay, I've cleaned stuff up over here just a little bit. And I left the 2 pi off of this, 2 pi coming from the 2 pi here. And the delta V, of course, being this, we get this expression. And then up here, I wrote this a little more clearly. Same thing as before. 3/2 is kind of crowding the r, but I left it the way it was. Should be readable. And the integral goes from 0 to r. See that 0 there's kind of crowding the parenthesis. Let me put that there. Okay. Now, the delta G contribution from the delta S disk at x is what we see here. And here's a picture just to remind us of where we are. The result for the entire cylinder is then gotten by simply letting the delta x approach 0 and partitioning the x-axis, letting this be a typical member of the partition. And in the limit, that's going to lead us to the integral you see down here. It's a double integral, which means that it's basically the integral with respect to x of this integral. So we can do this integral. It's not a difficult integral. We do it by, I'd change variables, let w equal big X minus little x, and you just get w over w squared over, well, you get a w here, you get a w squared here, and dx is, or delta x is just a delta w. Very easy substitution. But then you have to do a trigonometric substitution on that, and you might or might not be up on how to do that, but it's a standard first-year calculus topic, so you should know how to do that, or you should be able to review and do that. If I have time, I'll go ahead and do the calculus of the integral, but I'm not going to be able to do it in today. Okay. In any case, we have the inner integral, which is just this integral, and of course we've still factored out the 2 pi g rho. Put the rho in front of g here, and the I. So there's your inner integral, and then that integral is going to have an x in the result because we're going to be evaluating for r, not x. And then that is going to be integrable with respect to x, and that'll be from negative L over 2 to L over 2, and this is going to be our field. And that's something you should be able to understand based on first year calculus, that this is just an integral with respect to x of this integral.